Good evening, sir. Karthiganesh, sir.
Sorry, I am speaking mic meter. Do you hear me, madam?
Good evening, sir.
Good
Sir, we'll
evening.
start the session in another 10 minutes, sir. Let the participants count may reach to 100.
Sure, madam. Okay, madam.
Yes, sir. Okay, sir. Thank you.
Thanks, madam.
Let's start the session. Good evening, everyone. On behalf of the Division of Artificial Intelligence and Machine Learning, Karunya Institute of Technology and Sciences, Coimbatore, I welcome all of you for the day 3 sessions. Today's session will run from 6 p.m. to 9 p.m. The following are the instructions to be followed for the participants. There will be 2 sessions today. Only one feedback form needs to be filled at the end of the day. The feedback link will be shared at the end of the session. In between sessions will not be shared. Only one feedback form you have to fill, and that will be shared at the end of the day. Please note down your participant ID from the email communication because it is required for filling the feedback form. For technical queries, please post them in the chat box during the session. It will be addressed at the end of each session. Now I'd like to introduce the resource person for today's session who will be conducting both sessions. So we'll conduct both sessions today. Today's session will be presented by Dr. Karthiganesh Durai. He is the founder and CEO of Quantum G Research Labs Private Limited, Bengaluru, and the co-founder of Quantum Computing India, Bengaluru. And he served as a professor of practice at NIT, NITT, Meenakshi Institute of Technology, Bengaluru, and a visiting faculty in SRM University, Chennai, and VIT, Chennai. and the Naval War College, Goa. Currently, he is pursuing the Executive General Management Program, EGMP, at IIM Bangalore. He holds a Master in Computer Application from NILIT Bangalore and a Master in Business Administration from Puducherry University. He worked as a data scientist at Dell Technologies Bangalore from 2013 to 2022. His skill set includes COBOL, FoxPro, C++, Oracle, VB.NET, Big Data, Business Intelligence, Python, and Julia. Following quantum computing industry since January 2004, he has completed his MCA project titled Implementation of Quantum Computing Algorithm in the year 2010. 2010, he has completed his MCA project in quantum computing algorithm, and he has undertaken over 7 courses on quantum technologies from platforms like Coursera, edX, Udemy. With hands-on experience in major quantum hardware and simulators, he has been actively involved in building quantum machine learning-based solutions and conducting R&D since 2017. His expertise extends IBM Qiskit, Sanoda Panaline, Microsoft QShar, Cura Blockade, Amazon Bracket, and Quantinum Ticket. So Dr. Karthiganesh will be discussing 2 topics today. Topic 1 of session topic of session 1 is demonstration of the QML model, and topic of session 2 is demonstration of Qiskit. Welcome, sir. Now you can take over the session. Thank you.
Thanks, madam. Thanks a lot. Madam, can I exchange the sessions? I will start with the demonstration of Qiskit, then move
Yes,
to
sir.
QML. That will be
Yes,
more.
sir. It's up to you. It's up to you. No problem, sir.
Sure. Right. So thanks for the nice introduction. Thanks, madam. I believe, oh, there is 124 participants. It's really big.
At the end of the day, it is reaching to 256 daily.
Right. Amazing.
Thank you.
Amazing.
Yes, sir. Yes.
Feel free to stop me at any point of time. And this session is fully practical oriented session. Of course, if you have laptop, you can practice along with me, at least for IBM Circuit Composer and other programs. If not an issue, we will have, you will be able to follow along and understand the gist of executing quantum programs in any platform, maybe your local system or Google Colab, Jupyter Notebook, or directly running on the client system platform. So there are many quantum systems these days. I'm not sure. You might have heard that there are superconducting quantum computer, trapped ion, photonics, neutral atom, and annealer. These are all various types of quantum computers. And there are companies like IBM, Rigetti, IonQ, QEra, D-Wave, and AWS, Google. These are all offering quantum hardware. So whenever the quantum hardware is available, they are also offering quantum software. So considering quantum hardware and then quantum software as the platform, accessing quantum hardware is always costly. For example, if you want to access IBM quantum processor, they are offering 10 minutes per month free of cost. But if you try to access pay as you go model, they will charge $96 per. Madam, I need a screen share permission, madam. So,
sir, you can click on this share button. You can able to share now, sir.
Yeah, it is telling host disabled participant sharing screen sharing. I think you have to give me permission.
Multiple participants. Sir, now can you try from your end?
Yeah, now it is working.
Okay, sir.
So what we have seen of late is that the access to quantum computers are very costly. As I told you, IBM is charging $96 per minute. So obviously, assume that nearly $100 per minute. So if you want to run your program for 1 hour, you are going to burn how much? 60,000, correct? Sorry, 6,000 US dollar. 6,000 US dollar per hour. That is the level of money expected to practice in the real quantum computers. Okay, IBM is costly. If you go to AWS, AWS charging for their simulator, they are charging $2.7 per minute. And if it is the real quantum computers, they are charging per shot. So if you run a circuit with 1,000 shots, it will cost around $0.75, $75 per execution for $1,000, 1,000 shots. So considering all those things, all organizations are offering simulator. So now I'm going to demonstrate IBM Circuit Composer, which is one of the popular simulator. Let me put it here. This is the URL, quantum.ibm.com. This is the URL where you have to go here and oh my God, be able to access. If you don't have IBM Quantum account, you can create using this one. Okay. Yeah. Now actually I have to order security key authenticator. Let me do it because this one step last time when during the demo it was um, so I have to do this one. Give you a few minutes. I will activate my account here. This is one step I did some time back, but so when you are creating your IBM account first time, it is necessary to activate your IBM account using this kind of security application, MFA. Now I have to test my authenticator. Just it will be activated. Anyhow, this is one of the steps when you are creating, you have to do that one. So let I have to what's the step? Yeah, done. Is it working? Yeah. Is there any question? Yes, the simulator is free. And when you are having the simulator, yes, when if you want to create your IBM Circuit Composer or IBM account, you need to create your account in quantum.ibm.com. I will paste this URL in the chat window. That will be helpful. So go here, create your account. After you create your account, after activating your MFA, all those things, you will see a screen like this. You see here, up to 10 minutes per month is free. But if you want to upgrade, and open plan is what you are having free. But if you are going for pay as you go, 96 US dollar per minute. And if you are locking some time with the premium plan, 46 US dollar, then dedicated services like this. And in this one, it will show all the job you have executed so far. And if you scroll down at the end, you will see something called IBM Quantum Composer. Come to this IBM Quantum Composer, it will display your circuit designer. This is what IBM Circuit Composer. I believe more than 50% of this 167 participants should have this account, and then they already get their hands dirty, meaning that they already practiced some circuit in this IBM Circuit Composer. I believe my statistics are correct. If not, maybe that percentage will be reduced to 30%, 25 to 30%. But certainly those who are interested in quantum computing, some other time they might have experienced this IBM Circuit Composer. But there is a way to learn this IBM Circuit Composer. That is what I'm going to demonstrate for the next 30 minutes. After that, I will show a simple program using IBM simulator, IBM Qiskit simulator. So this IBM Circuit Composer is running on their cloud, IBM cloud. So whenever you are running, it will directly hit the real quantum processing unit, QPU. So whenever you are starting IBM Circuit Composer, first thing what you have to do, give the name to the circuit. 25, 0 to 12. Sorry. 1. This is my circuit name. Here, what the important portion is that this is your operation, but the most important part is this circle and blue color and then vertical line, which is called phase disk info. This phase disk info is the most important part of your IBM Circuit Composer. So always pay attention to this one, what it is showing, because that gives you the states of qubits. And initial, those who are starting IBM Circuit Composer, they should go to, if you click file new, it will create a new file. Already we are in the file. Go to view, come to this panel, keep only the graphical editor. Remove everything else. View, panel, probabilities, view, panel, QSphere. You should not see anything else except operation, the circuit designer with the phase disk info, because this will reduce the distraction. Am I right? This is the first step. Make sure that you are removing all output windows. Then go to edit menu, come to manage register, make this as 1 qubit and 1 classical bit, meaning that we are going to practice with single qubit operations. And remove, if there are anything else, remove them. You can click and delete like this. So this is the plain single qubit circuit. Now, if you see the operations, many multi-qubit gates are already disabled. Remaining things are your single qubit gate operations. Don't touch H now, Hadamard gate now. Take this one. This gate is called, see, whenever you see a gate, you may not be able to understand what is this gate. It is come. That time you click this one, it will show the gate symbol or gate icon and the name of the gate. This will help you to understand what operation you are doing. So the NOT and identity, T, S, Z, T dagger, and measure, reset, barrier, control, and last phase disk. Let me start with the phase disk, because I told you in the whole screen, phase disk info is important thing. Right click on here and it will show the info. If we click info, it will explain what is this phase disk info. In the phase disk info, the blue color indicates the amplitude. The line, the off line indicates the phase. And then there is circle. That circle indicates the entanglement. So there are 3 aspects of any qubit: amplitude, phase, and entanglement. All these 3 characteristics can be observed using this phase disk info. Any questions so far? Yes, it is free, sir. Santosh Kumar Rajshekhar, sir. It is free. Okay, cool. I recommend use your universal ID, university email ID or organization email ID, because personal ID is not encouraged by IBM. Even if you see while creating, they mentioned work email only. So better use your university email ID. Hope that answer your question. Any other question? Feel free to ask the question, because questions are more important part of learning. And we are not in hurry to complete the syllabus. It is a learning process. I ready to answer all of your questions. So feel free to interrupt me any point of time. I will answer a question, then move on to the next step. Now you understood, right? For any gate, you can right click on the gate, click the info. That will show you the explanation. Most of the time, you can't understand. See, for example, if you click on the right click and click info, it will explain something, but you will not able to understand unless you have fundamental concepts very strong. And there will be one link which is called Qiskit API reference. If you click that one, that will open another documentation that will be helpful. That's why I told, oh my God, what happened? Now you see the X gate. Now you remember the icon shows at the cross and circle. The name shows not, but the Qiskit reference shows X gate. All three are same. These are all rotation over X axis. How it is achieved with the help of this matrix. So a qubit state is multiplied by this matrix. That is what you are getting the output. Now you may get confusion how this matrix is gives the different value or different state. That's what I'm going to show now. Imagine that now, as I told you, don't touch H now because that needs special attention. Just drag and drop here. Now you see the rightmost phase disk color changed to full, which means now your qubit is in 1 ket. Earlier, if I remove this one, your qubit is in the 0 ket. You see the probability of 1 ket equal to 0%, which means your qubit is in 0 ket. If I put not gate, it will become 1 ket. So this is the way how IBM Qiskit is displaying 1 ket or 2 ket. Now, let me try some other gate. Let me try this U gate. U gate will be very complicated. Okay, I will try U gate. If I put U gate, you can see the phase is changed to 3 pi by 2. And imaginary part is -1. Probability of 1 ket become 50%, which means now your qubit is in a superposition. So by applying various gates, you can change the state of your qubit the way how you want. So learning quantum computing is nothing but understanding the impact of these gates on your qubit. If I apply S gate, let us see what is doing. So it is changing the phase from 0 to pi. Now let us remove this one. Now you see this is phase is 0. But if I apply S gate, you will observe that the phase is changing to pi. So if you want to understand what is this S gate, what you can do, you can right click on the S gate, click the info, and you can read this one, understand to some extent. Still it is not clear. Go to Qiskit API reference, which is showing the underlying matrix. So the Qiskit is transformed using this matrix. That is the reason why phase of the qubit transformed from 0 degree to or 0 radian to pi radian. Is it clear? So my personal recommendation is that take 1 or 2 days, experiment with all gates and respective matrix. I usually recommend all the students when I'm taking the long-term course, I will ask them to write gate name, gate icon, draw the gate icon and the matrix. I will ask them to prepare a table, gate name, draw the gate icon and then note down the gate matrix. So for all gate, they have to prepare that one. and frequently I will make them to review that particular list frequently, which will make them to become familiar with all gates and corresponding matrix operations. Now, as I told you don't touch X gate, right? Now, sorry, H gate. Now, imagine that now the whole state, it will go to a different level when I apply Hadamard gate. So Hadamard gate is, if you start your qubit with a Hadamard gate, your qubit will start in a superposition. Any small operation will impact differently. So any gate sequence without Hadamard gate will give you different state. With the Hadamard gate, it will give different state. All these things you can explore and visualize. That is the power of IBM Circuit Composer. Why I recommend everyone to start with IBM Circuit Composer? You can visualize the impact or the transformation of gates onto your qubit. Is it clear? Any question? I will answer the question. Please save the recording. Sir, does it generate the random number? As it is, no, it is not a real random number. The random number generated by simulator, they are all pseudo random number. They are not real random number. And there is another question, it is not related to me. And okay, right. And in the Q&A, there is one question. Okay, no open question. I will answer live. I will close that one. Done. Right. So now with this as a introduction, now you know what to do with IBM Circuit Composer. Play around. See, I recommend play around with more than 8 gates initial time. Never hesitate. Don't worry about what is this gate, how it is working, what is the matrix, all the impact. Don't worry initially, because the goal is to become familiar with this IBM Circuit Composer Designer. If you have more gates like this, the phase disk info shows the final state. But I want to check gate by gate or layer by layer. I can switch on this inspect. Now you will see a player control. If you click the next layer, it will show layer by layer. That time for each layer, you can observe the phase disk info. You see the phase disk info. Now it is superposition. Now it is in the NOT gate. Now it is in the S gate. Now for T gate, S dagger, Y gate, RX rotation, U rotation, identity, which will remain same, then T gate. And if you click inspect, it will stop. So the inspect is used to observe your gate operation or your circuit operation layer by layer. So each gate is called layer. So for each layer, if you want to differentiate certain operation, you can put this barrier. For example, this is one step, this is another step. So you can put a barrier to clearly show that these are the different steps, these are the different steps. But anyhow, internally, these are all one single unitary operation. And after assume that this is my circuit, I complete it. And I want to run it. Where should I run? You have to go to setup and run. When I click setup and run, it will show, it is telling on 19th it won't work. Okay, no problem. And it will show you three QPUs. One is IBM Q with 0 jobs, and Sherbrooke 5 jobs, and IBM Brisbane 37. So you can choose, I want to run in Q and run on IBM Q, but it will throw an error. Circuit needs at least one measure. So when you design a quantum circuit, there should be one measurement operation, which is this one, measurement operation. So the measurement operation, now if we click setup and run, and it will run. Now please note this number 1024. This is called number of shots, because the circuit will be repeated 1024 times. And if I click, it will, what it is doing, you see the rotation, it is now submitting this job to IBM. So IBM will put jobs like this in a queue, because There are worldwide, globally, many members are submitting the job. So that will send to a job queue. The job queue will be here. After some time, it will be executed. If you want to know more information, you can click there. It will show when it is submitted, it is in progress, and completion. All those things will come. Sometimes it may finish in few seconds. Sometimes it may take few hours. It depends on our fate, or at the time what is the workload running on the IBM QPUs. That is the real reason, because if the IBM queue is very busy or for any reason it is down, you won't see the result immediately. So now this is the process to submit your task to IBM Circuit Composer, from IBM Circuit Composer to any QPU. Is it clear? Any question here? I would answer your questions, then move on to the next topic. What is RX rotation to apply? RX rotation is, there is no RX. Oh, here is RX rotation, right? If you right click the RX rotation and click, it will tell RX get implement e power iota minus iota theta over 2 times x. So the Qiskit, if you want to see the matrix is cos theta over 2 minus I sin theta over 2 minus I sin theta over 2 and cos theta over 2. Now you will wonder, what is this one? Uh, what is the meaning of this one? E power, why e power minus iota theta over 2 times x is translated into cos theta over 2. For that, there is a mathematical derivation, but I would like to tell you this one. Let me go to the last slide. Hope you are seeing my screen. Okay, let me take my pencil. See, all of us know, right? The psychet equal to alpha 0 ket plus beta 1 ket. We know this formula. Alpha psychet is the linear combination of basis states. That is what the mathematical reason. But the psychet can also be written like this. Psychet equal to cos theta over 2 0 ket plus e power iota 5 times sin theta over 2 times 1 ket. This is another formula for psychet. So obviously, considering the various forms of complex numbers, we can use either Cartesian complex number or polar complex number or exponent complex numbers. So combination of all those things will result in various matrices, complex number matrices. So the RX rotation mathematically, a rotation over x-axis, which is achieved by applying cos theta over 2 is the major, and negative iota sin theta over 2 as the other elements in the matrix. So that is because these are all unitary matrices. So the diagonal matrices cos theta over 2, the other things are 0, then it will become how to say, a rotation over x-axis, and then these rotations will make your orthonormal basis to collapse to basis states. So when you apply this one and you measure, that will collapse to 0 ket or 1 ket. That is the reason why these things are designed with negative iota in the non-major control or non-major components. Okay, that is the deep mathematical explanation. If I go deeper into that one, I think it is not the focus for this demo. For this demo, let us focus on IBM Qiskit. But feel free to ask me more questions if you have. I will try to answer. Cool. I believe no questions. Now coming back to the circuit. Now coming back to the circuit, still it is running, you see here. Let us run it. So now we know that the single qubit is very clear. Let us move on to double or two qubit circuits. What we have to do? I can create a new circuit, file new, and here I can change it to 2502 12 yeah, 2. So this is my second circuit. Here I need only two qubits, so I'm going to edit and manage register. Make sure your number of qubit and number of classical bits are same. That is the important condition. And here assume that I want to create a belt state. Belt state is achieved with the help of Hadamard gate followed by controlled NOT gate, CX gate, and measuring these two gates. This is called belt circuit. Okay. Now, after designing the circuit, it is appearing like this. But if there is no measurement, the circuit, see, it is still in the entanglement, which means the measurement always collapse your state or your qubit state to the basis states. See, now the qubit is in superposition. How I am telling? Of blue color. Of blue color is superposition. But the moment I put a measurement, you can see here that collapse to basis state to the 1K. Now, sometimes when you have multiple qubits, it may be very difficult to observe the phase disk and understand what transformation is happening among those qubits. That is when you have to go to view, come to panel, start QSphere. The QSphere will display the blow sphere, and another output is state vector. Another output is probabilities. So initially, if you want to understand these operations, I don't recommend to start with the belt state. Remove all gates. See, now I have two qubits, right? And if you see the QSphere, it is there in the 0, 0 kit. If I have two qubits, I will have four states: 0, 0 kit, 0, 1 kit, 1, 0 kit, 1, 1 kit. Now you will think it looks like binary. Yeah, it is binary. It looks like binary, but it is not binary value. It is states. That is what you have to remember. We are talking about states. It is not just 0, 0. It is 0, 0 ket, which means it is a state. So when I put ket, it become a vector. Vector is the state of your spin or polarity or any other characteristics, fundamental particles. Characteristics of fundamental particle. That is the correct sentence. So now, if I put Hadamard gate, what it is doing, you see the last bit is in both 0 and 1, which means you have both 0, 0 and 0, 1 as your possible states. And if I add Hadamard gate to the second qubit, what will happen? The second bit also will become 0, 0, 0 and 1, which means you will get four possible state at the same time. So that is the superposition of two qubits. Now imagine that I want to experiment with three qubits. I can click here and then plus, and click here plus. Now I have three qubits. For three qubits, I can have 8 possible state at the same time. Now you can observe that. Here one warning. When you see these lines, it may look like one line, but actually these are 8 lines. And moreover, in the Q sphere, you should not look into the line, you have to look into the state. The line is to indicate the connection from origin to this one. But you have to observe only the dot at the surface. The line is just a guide. Don't get distracted because of the line. Line is not important here. Now, I will try to apply a dagger, D dagger. Now, if you see the D dagger, only those middle lines become different color, and try to apply S dagger. Now you see the wherever I applied S dagger, those states become a green color, or not green color, it is orange color, which indicates the phase is somewhere here. So the color of this states indicates the phase. You got the point, right? So now you will realize there are a lot of things there in circuit composer to observe when you are designing a circuit. And it is really a good way to learn the state transformations. Hope you are all trying to get some more information than the usual circuit composer. Any question here? I would like to stop here and answer a question if you are having. Feel free to ask me the question.
Uh, Participants, kindly post your questions in the chat box.
Yeah, please. Okay, while others are asking the question, I want to show one more thing. Now imagine that I'm applying this P gate. P gate is one parameterized rotation. If you see the P gate, this information phase gate, it is the matrix for P gate is 1 0 0 e power iota theta. See, now the e power iota theta for 2 qubit, it works like this. Now, oh sorry. Now what I'm doing, the pi by, if you click this one, you will see the pencil symbol. But in Hadamard gate, if you click the pencil symbol, it will show only Q0 and add control. But for P, if you click the pencil symbol, it will ask you the lambda, meaning that you can change the theta of or lambda of the rotation. I can put pi by 4. So that time you will see the rotation is different. Say earlier it was pi by 2. After change, say now let me put it pi by 16. Now you will see this is pi by 16 radians. You understood, right? So it is possible to change the parameters of any gate. And this is essential to understand parameterized quantum circuits, which is called a PQC. And in quantum machine learning, you will come across a lot of PQCs. Those PQCs are depending on changing the lambda, theta, or there is one more, 3 parameters. Let me put it into the P. In P gate, you can see that one. Sorry, U gate. If I get U gate and click this one, you will see theta, phi, and lambda. These are the 3 parameters. You can change it. Is it clear? So here I can change this to pi by 2, this to pi by 4, and this to pi by 8. So I can change it whatever way I want. Then I can control the way how I want to transform the qubit states. Please remember, quantum computing is nothing but matrix transformation. I will start with the 1 0 0 0 or whatever number of qubits 0 ket. Then I will apply various quantum gates which are transforming the 0 ket to different states. That's it. Very simple. Quantum computing is nothing but state transformation. What is the use of 3 qubit over 2? Oh, okay. So it depends on your circuit. For example, if you are building a circuit for iris dataset, iris dataset has 4 parameters, right? 4 independent variables. We will use 4 qubits. You are using some other dataset, for example, a motor car, which has 12 parameters, then you can use 12 qubits. So this is one easy to understand example. So the number of qubits, you will make a decision. For example, if you are running a Dai-Josh algorithm for 4 qubit, you will add one more ancilla, so 5 qubit. If you are building a Simon's algorithm for 3 qubit, Simon's algorithm need 2n. So if there are 3 qubits, you have to add another 3 qubits as the ancilla. So you will build 6 qubit circuit. So the number of qubits is decided based on your problem and how many ancilla qubits you need for your problem. Does it answer your question, sir?
So there is only one question left out. What's the use of 3 qubit over 2?
Yeah, that's what I answered now, madam.
Okay, sir, over.
Yeah,
After
that's what
there
I
is no
answered.
more questions.
Cool. So now I will give you a suggestion for your practice. Before that, let me check what is the, see, still it is running. But it is going to run for only 2.2 seconds. And we have submitted with 6.32. Now what is time now? 6:48. So it is running for waiting in the queue for 6 minutes. But before we are completing our today's session, it will be executed. Right. This is very clear for everyone. So my personal recommendation, spend good amount of time in IBM Circuit Composer. Try to understand the qubit gates, their respective matrix, and visualize the transformation both in phase disk info and any other comfortable user visualization. See, there are 3 visualization: QSphere, state vector, probability. I personally prefer probability. Sometimes I will use state vector. I rarely use QSphere because QSphere I know very well. When I'm doing some operation, I know visualization. I can easily visualize where that qubit state will go. So I won't use QSphere frequently. But for beginners, that will be helpful. I think there is one more question. Let me check the question. Can you give crypto related examples? Crypto related example, today's session is QML. I will give you, but this one is now what I'm giving now is the demonstration for IBM Circuit Composer. So I want to keep it domain agnostic, meaning that I'm not going to attach any domain. So when I go to the QML examples, I will include cryptographic. For example, Shor's algorithm. Shor's algorithm is not allowed. It is a combination of quantum Fourier transform and then quantum phase estimation. So like that, when I will include that one. Okay, but not now. After the circuit composer is over, I will. So now, next guideline for you to learn IBM Circuit Composer. Go to Google or any browser or any search engine, whatever you like. Search for sample quantum circuits and go to the image section. You will see lot of circuits like this. Try to recreate these circuits. Don't worry about understanding. Don't try to understand the circuit, what the circuit is doing. Just to try whether you are able to reproduce this circuit. See, now take this circuit, example of 5 qubit quantum circuit. Now, if you want to reproduce, how will you reproduce this one? I will show you. See, if you take the CX gate here, it is connecting 0 and 1, but I want to connect 0 and 2. I have to click this edit and change the target qubit to Q2. And if I want to change another qubit, I want to change the control qubit is Q1, target is Q0. Click here. Control is Q1, target is Q0. Then the circuit will go this direction. So like this. And if you want to put a layer, say for example, barrier, click the barrier, click the edit button, check these things. It will put a barrier like this. So try to, without understanding the circuit, first become familiar, become fluent in the Qiskit composer operation. That way you will be able to design lot of circuits comfortably. Then after some time, you can try understanding those gates by manually performing the matrix multiplication. And I'm not sure how many of you have that much of time. If you don't have time, please assign this task to your student who wants to pursue quantum computing, then verify their output. That way you can delegate the laborious or the time taken work to your mentee or your student. Then the final result will be useful for you to get it. Okay. But frequently work in IBM Circuit Composer, even though you become expert using the Python program or Jupyter Lab. No, IPy and B5. Okay, now we are going to stop IBM Circuit Composer. Okay, right. Now, with this Qiskit, IBM Circuit Composer, we spent considerable time here. There is a reason. After designing this, if you go to View and click Panel and Code Editor, whatever you have designed, that will appear as the Python code here. Make sure this is showing Qiskit. Sometimes it will show open cosm. You will see code like this. So make sure you are seeing Qiskit, which is the Python code. You got it? This is the IBM Circuit Composer generated code. This code you can use in your Python program. Is it clear? Any question? This is IBM Circuit Composer. We are ending IBM Circuit Composer now. Okay. There is one more question. How do we give the class variable in supervised learning with the qubits? Meaning that binary classification or multi-class, right? Your question is related to output, right? Nirali sir or Nirali madam, I'm not sure. Okay. So depending on the number of class, if you are using a quantum neural network, you will mention the measurement, because in quantum neural network, the measurement operation will give you collapse down to basis states. Then the number of qubits, for example, this is reversible gates. The number of qubits input will be number of output. So when you are planning to build convolution neural network or normal neural network, the output layer in classical world is implemented as measurement. So even though you have 6 output, you will measure only the function register rather than the ancillary register. So the function register you can choose depending on the class. If you have 2 power n classes, you have to identify n qubits. So if you have binary classification, you have to measure only 1 qubit. If you have 3 class or 4 class, you have to use 2 qubits. Anything above between 5 to 8, you have to use 3 qubits, like that. So 2 power n class, you have to use n qubits. Yeah. And selection of qubits is very important. Which qubits you are going to measure? That you will decide based on the ancillary operations, how your hidden layer is processing. Because I will explain when I explain the QML demo. That time I will clearly explain how to identify those things. Okay, right. Any other question? Okay. If no more question, I am going to stop Qiskit Composer. Now I am going to write a program. Now, to build a program, I follow Visual Studio Code with my local simulator. I will show you what is my local simulator. I will go to command prompt. Say actually this one is Windows, but my production system is Linux, so I will use Linux. I have, but here also for demonstration purpose, I have some environment. See, for example, QK132. So what I will do, env QK132 scripts activate. Now I have activated my environment, Python environment. And if I type a pip list, it will show my Qiskit version or any other version. If you see here, my Qiskit is 1.3.2 and then Qiskit AER is 0.16. I already installed Qiskit simulator in my local system. Since I have this already in my system, it is easy for me to run a program. So let me go to clients mkdir Karunya, CD Karunya. Yeah. Here I'm going to create my program. So I will use my Visual Studio Code, Control K, Control O, D drive, clients, Karunya. Yeah, this is my folder. I have selected this folder. Now here I'm going to type my first program. So click this one, first.py. So what I will do, see here, for easy purpose, see, this is the code I generated, right? In my Qiskit, I copy this code and paste here. So here, I have to measure and draw. So circuit dot measure q reg comma c reg, and after that I have to draw circuit dot draw MPL mode, what's called matplotlib mode. So obviously I have to import matplotlib dot pyplot as plt, and here after the show plt dot show, then only it will work in the command prompt, otherwise it won't work in the command prompt, because most of the time you may use Jupyter notebook. In Jupyter notebook the draw will draw, but in command prompt the draw will not work here. So now I will come to my command prompt here, Python first.py. So it will take some time. Now you see the circuit is drawn here. So whatever, if you recall, this is the same circuit, right? So it is whatever you are designing in your circuit composer, you can write your own program using Visual Studio Code. So this is the method I follow. But now what I have done circuit only. I have not executed it. Remember in circuit composer, I went to set up and run and then executed. That step I have not done here. So if you want to do it in a simulator, you have to do like this. Sim equal to, okay. For a simulator, I have to import from Qiskit AER, import AER simulator. And let me import. Okay, now I have to sim equal to AER simulator and job equal to simulator run this circuit. And the job will give you the result. Result equal to job dot results and output equal to result dot get counts. Then this is result, not yes. Okay, right. Now let me print output. Okay. So this section will draw the circuit, right? And this section will will execute the circuit in my local simulator. If I want to run it on a real quantum computer, I have to follow a different approach, meaning that only the simulator need to be changed to um, IBM Qiskit runtime, and I have to create a sampler that I have to pass. So that I'm not executing now. First, let me do this first. Oh, still it is running. Oh, okay, because this is on, so that is the reason why it is not closing. Okay, now let me run this. I will close this, then only it will run the next. Now you see the output. It is 3 qubit. So 0, 1, 0 is 271, 246, 214. But this output doesn't make sense. So obviously I need some visualization. So what I'm going to do, from Qiskit.visualization, import plot histogram. This is my visualization function or class for drawing plot histogram. So now I have to plot histogram with this output. Okay, now what I'm going to do, I'm removing this PLT show from here because that is stopping my program executing. I will add here. Now let me execute. Yeah. Now you will see this is my circuit. See, personally, I prefer this kind of approach as it gives me more flexibility compared to running on a Jupyter lab, because from here I can save as a file or keep this as a follow purpose, all those things. Okay, this is what the demonstration of Qiskit using Pi5, not the Jupyter lab. And why we have to follow this approach? For beginners, this may look like, oh my God, this much of steps. I should have a virtual environment. I have to run into Python, then come to command prompt and run it. But this is how professional system is being built. Professional systems are not built using Jupyter Lab. Jupyter Lab is used to build prototype, meaning that, yeah, this algorithm is working. We can check, discuss. After that, when you go to client, we cannot give the Jupyter notebook. That is IP. You are exposing your IP. Obviously, you don't want to expose your IP, right? So when we build a solution, we will use only this approach. That is the reason why I demonstrated this approach, because most of you might have seen the Jupyter notebook already. Okay, I'm answering question. Is it here 3 qubit? Yes, 3 qubit, 2 power 3, 8 states. Make sense? It is same as binary. N bit will give you 2 power n, right? But in binary, n bit will be in any one of the 2 power n at any point of time. But in quantum, n qubit will be in all 2 power n possible states at the same time. For your benefit, I will type that statement, what I'm telling now, because it is very difficult to comprehend when I speak. Let me put it here. This one really will be helpful for you to understand. In classical, let me put digital computer. In digital computer, n bits will be in raw mode is also there. That is the reason why it is not working as expected. Okay, right. Okay, let me increase the font size. In digital computers, n bits will be in any one of the 2 power n values at a given point of time, say t0 or t1, right? In quantum computer, In quantum computer, n qubits will be in all 2 power n states at a given, not at a given point of time, simultaneously. Simultaneously. 1 minute. Sorry. So this is the statement you have to understand without any doubt. Is it clear? Anyone have any question on this statement? I am expecting a lot of questions. But what the graph represents as the count? That's a good question, Santosh sir. I will answer. How quantum-based circuit check the practical analysis? Okay, I will answer these 2 questions. First question for Santosh Kumar sir question. But how is the graph represented as the count? Now you see the point simultaneously 8 values, right? Because the 3 qubits, 2 power n will be 8 values. If you see the graph, all 8 values are having ಇಲ್ಲಿ. ಪರವಾಗಿಲ್ಲ. So now the whole circuit, if you add all these numbers, let me put a calculator. See what is the number? 10 plus 223 plus 244 plus 11 plus 247 plus 21 plus 11 plus 257. What is the number? 1024. Remember, when I submit the job, there is a box called shorts. In that shorts, there is a 1024. So I executed the circuit 1024 times. Out of the 1024 times, 111 came 257 times. So 257 over 1024, that is the probability of 111. Now you understood, right? Where probability comes into picture. So the all 3 states will be, sorry, all 8 states will be in same time, but different probability. That is the thing you have to understand. So remember, when I designed the circuit, when there is the 3 qubit, all 8 states are there with different probabilities. That is how quantum computers are offering parallel processing capability. Does it answer your question, sir? Santosh Kumar, sir? Okay, now I am trying to answer the probability. The meaning that the each state will be in different probabilities. If you want to write it as a statement here, okay, let me explain here in the another new workbook. See, for example, 00 kit and 001 kit and 010 kit and 011 kit. Like this, I will have multiple things. So here, the probability P1, probability P2, probability P3, probability P4, like that, there will be P8 probability. So 8 probability. At the end of the day, it should be sum of square of probabilities equal to 1, which is mathematically written as sigma P I square equal to 1. And remember, that is the reason why in this expression in here, alpha square plus beta square equal to 1. If you read many of the quantum literature, you might have seen this one. The psi ket equal to alpha 0 ket plus beta 1 ket given alpha square beta square equal to 1. Why? Because the states will be in different probabilities. If you have n qubit, you will have 2 power n states and 2 power n probabilities. Sum of all 2 power n probabilities, sum of square of, because these are all not probability amplitudes. That's the reason we have to square them. So sum of square of probability amplitudes should be 1, which gives the normed vector space condition. Any question? Hope, sir, I answered the question. Why most of the cases we are using ket values? Why not we'll use bra values? The states are ket only because column vector. But bra are their duals, meaning that they are row vector. In the how to say, when I say, okay, for that, that's a good question, really very good question. You know Bloch pair, right? Most of you know Bloch pair. So let me take the Bloch pair as an example. So my Bloch pair, let me take this like this. Okay, this is z axis, z axis, x axis, y axis, and here it is north pole. Here it is north pole. Here it is south pole. Sorry, south pole. So when I say 0 ket, which means my spin position is in the north pole, it is not in the south pole. So I use a column vector to represent the states. So, but I cannot mention 0, sorry, it should be, but if I mention a bra 0 is not the state. It is the dual of this one, which is a row vector. 1, 0. And it's not actually 1, 0. It is 1, 1. See, actually, this also very, very interesting fact is that we are thinking that it is 1. It is actually, it is not 1. It is 1 plus 0i. Originally, this is the real data behind all quantum numbers. All quantum numbers are not binary. They are, if the imaginary part is missing, they are 0i. Oh, sorry, 0i. Right. But here it is 1 minus 0i. And this one is 0 minus 0i. So anyhow, since imaginary part is 0, we are ignoring. That is the reason why the ket values are looking like binary, but they are not binary, they are complex numbers. The fact is the imaginary part is 0, so we are ignoring them. So the state is column vector. The dual of the state, which is not physically happening, it is happening in the dual only. That's why we are not using bracket. Sorry, bra of 0. Sir, does it answer your question? Yeah, correct. The complex conjugate is 0, so we are ignoring in the binary things. Cool. Hope that answered your question. Very good. Any other question? Feel free to ask the question. That's where a lot of learning comes. Now coming back to the program demonstration of circuit Qiskit. Let me. Do you need me to demonstrate Jupyter Lab? Okay. If you want to work, it is not always for everyone. It is possible to build these circuits, all those things. So we need to make sure our Jupyter Lab is ready. So for the Jupyter lab is ready, what we have to do? We have to pip install Jupyter lab, then it will be ready. For many beginners, I recommend go to Google Colab. If you have, obviously everyone is having Google account, collabresearch.google.com. I will paste it in the chat window. So here you can create a new notebook, file new notebook. What happened? My bad. Collab. So I will click new notebook. Here I will do the same operation. I will execute here. So Google Colab is come with the 8 GB instance. So if you are writing advanced program, it will fail or it won't run. Considering that as a fact, if you are doing something for your project and all, better go for paid version of Google Colab. See, when you do this one, Google Colab will throw a lot of error because it is not having those packages. So obviously what you have to do, you have to pip install those things. You see here, it is telling I don't have Qiskit module. So obviously what you have to do, pip install. See, it is automatically identified Qiskit and AER. And along with that, you have to install PyLatex ENC also. These are the three things you need if you want to run your program in Google Colab. So I will paste these commands also in the chat window because please take a note for this one, take a copy. Oh, there is a question. In general, quantum circuit reversibility is possible, but most of the quantum based circuits, the space of the circuit is increased when you implement large circuits. Sir, may I know the reason as per the VLSI principle? Sir, the space, when you refer to VLSI principles, with in context to VLSI, the space of the circuit, I'm not very clear, sir, because um, in the context of VLSI, I'm not able to connect the space, whether you are referring to the physical space or memory space, that is not very clear. Um, can you give little bit some more information, sir? Because the context I am not able to understand. Because the space of the circuit is increased means I'm not able to clearly connect, sir. You add some more points, sir, then I will try to answer the question. Because I'm not good at VLSI. Maybe that is the reason why I'm not able to connect the question with the context. Okay. I will answer this question after some more additional information, sir. I'll also rephrase the question and then ask me, sir. Okay, let us continue with the Google Colab approach. So after you pip install these things, it will take some time, and then Google Colab, for each notebook, you have to run these three commands every time. So that is little bit painful task, but you have to do that one. And sometimes if you run, sometimes it may not work. At the time, you have to go to runtime and then restart session. But in this case, it won't, it is not required. It will work fine because I know. So now all those things are imported. Let me create these things. Now you'll see the circuit and run this AER simulator here. Let me run the plot histogram. Actually, here I don't need PLT show. Yeah. So you can do, but this time you see different probabilities. Yeah, that is the nature of quantum computing. Each time it will run. Even in the same notebook, if you run again, it will show different probabilities, different outcome. So this is how you work in Qiskit. This is the demonstration of IBM Qiskit circuit composer, IBM Qiskit simulator in the Python file in your local system, or Google Colab notebook on the cloud. All those things I demonstrated, the three set of demonstrations. Any questions? Hope this is clear. This 1.5 hour session. Now we will yeah, yes, everywhere. Any cloud-based Jupyter notebook, you follow the same process. Yes, sir, correct. Cool. Madam, what is the break time? Because now it is 7.
Yes, sir. Sir, we can give 10 minutes break after this session. So
Yeah.
10 minutes break. The 7:30 we used to give closing for session 1.
Okay, sure. Okay, right.
Okay.
So there are many programs what we can do it here in this model, and the Dijosha, Ben Srinivasarani, and Simon's quantum Fourier transform, quantum phase estimation, BB84 quantum key distribution, or E92 quantum key distribution. And all those algorithms you can do this way, or Jupyter Notebook, whatever you feel comfortable, you can do. But production systems, always Python 5, no Jupyter Lab. Clear? Okay, right. Cool. Oh, sorry, I forgot to. Oh, there is another question. Feedback for this session. Oh, okay.
So end of session 2 only feedback form will be shared. So please stay back.
Okay, sure.
So shall we go for a break?
Yeah, I think if no questions, we can go for break and then we will come back into 5 minutes. Sorry, 10
Yes,
minutes.
sir. Yes, sir. 10 minutes. So participants, you can take 10 minutes break. After that, we can continue session 2.
I will stay in the call, right, madam?
Sir, you can also, can continue be in the
I will
call.
stop and mute, madam. Stop my video and then mute.
Yes, sir.
Okay, thank you. Bye. Excuse me, madam. Can we
Sir,
start?
yes, sir, we can start the session.
Okay, sure. Let me share my screen. See, now we are going to see the demonstration of few QML models. First, I will start with quantum support vector machine, then quantum convolution neural network. Uh, if if we have remaining time, we can see any other possible models. Okay, right. So let me download some of the models. Because I have to download to my local laptop. Mm, Here. Let me download this iris and let me download QSVM. So these things are downloaded to note download folder. I will copy them to our folder. So I believe all of you know what is iris dataset. It is the flower dataset from South America. So for the classification, we will do both classical SVM and quantum support vector machine. And this one is Jupyter notebook. So I need Jupyter lab in my uh, local laptop. So here Jupyter lab is not here. So I have to pip install Jupyter lab. Oh, sorry. I should not give like this. I can run this in Visual Studio Code also, but I want to show you if you don't have Jupyter Lab in your virtual environment, how to install that one. So after Jupyter Lab is installed, you can start your Jupyter Lab and then run the program. And also I will show you how to check the various component in the Jupyter notebook such that that will give you the debugging capabilities. There are questions. Oh, sessions to start. Okay, right. Yeah. Now here I have to start my Jupyter lab. Jupyter lab. And I believe you know what is the meaning of Jupyter. It is Julia Python terminal. So now my Jupyter lab is ready. Here I have my program. So let me open this QSVM i5nb. And here I have scikit-learn because I need scikit-learn. Let me install scikit-learn here. Qiskit already I have in my local virtual environment. So I'm installing scikit-learn and then Qiskit algorithm also I will install. Installed. Yeah. Then Qiskit is there. So I'm going to install only Qiskit algorithms. So these are the preparation steps for the first time. So we have to do all these things. Then Qiskit machine learning. Yeah. So I have installed scikit-learn and Qiskit algorithm and Qiskit machine learning. All are installed. I need matplotlib already there. I need Seaborn and pandas. Okay, all are installed. I'm right clicking here and removing all outputs such that it will be more cleaner. So what I have done, I have installed pip installed scikit-learn algorithm, Qiskit machine learning, Seaborn and pandas. And now let me import all the packages. The first one is classical model. After that, I'm importing packages relevant for QSVM, which is coming from Qiskit library ZZ, which are sampler and compute fidelities. Let me run this. Now I'm reading CSV using pandas read CSV, which is stored in DF iris. And this is my iris dataset is 150 rows and 6 columns. From the 6 columns, I am taking sepal length and sepal width, petal length and petal width as the data, species as target. And using those iris data and iris target, I'm creating train and test split. I believe most of you know what is train and test split. If you don't know, let me know in the chat window. I will explain them. Yes, we need 4 qubits, sir, here. Correct. Exactly. So with this one, I'm going to run a classical support vector machine, which you got output immediately. And the confusion, this is the confusion matrix. And here is the output as 0.98% of accuracy. And the given data 4.4, 4.4, 4.4, 4.4, it identified as Iris virginica. So the classification gives us the Iris virginica. So the classical part, straightforward. I created a support determination model using SVC, which is coming from scikit-learn. So if you want to learn what is SVC, go to the documentation of sklearn SVM. Like this, that will open up scikit-learn SVC. Here you can understand what is the SVC. SVC is the C support vector classification, and that hyperparameter C equal to 1.0. All those things are explained here. You can learn from this documentation. I recommend learn from this documentation because that will give you the updated information. Now, since classical is completed, now we have to go to quantum. In quantum, we have to create a Doug dimension And for the ad hoc dimension should be 4. Okay, let us run with 2, and later we will increase the actually it should be 4. Ad hoc dimension 4, and it is telling some deprecation error for sampler. It's okay. Now we need 4 component. One is ZZ feature map for the angle rotation, sampler for execution, compute and uncompute for fidelity. This ZZ feature map and this fidelity are used to create kernel. That is using fidelity quantum kernel. After creating all these objects, we are importing the quantum support vector machine from this library, Qiskit machine learning algorithms, QSVC, and the same model, classical model, how we are creating the model, then fit and predict, then confusion matrix, classification matrix, then predict for the unseen data, your new data. Same structure here. SVC fit and predict, then confusion, classification, then prediction of the new data. Okay. So the same format I'm using here. Now you will observe it is taking more time and then accuracy is also less. So now you'll wonder quantum is claimed to be more powerful, more accurate, all this. But when you run a model on a simulator, it is returning, it is taking more time and it is returning less accurate output. To justify that one, we can understand that quantum is in the first thing we are running on a simulator. Next one is even you run on a real quantum computer, you won't see more what is called a much better improvement because quantum computing is in the nascent stage and it is not when you benchmark it with the state of the art classical, it will not outperform the classical model. So at the current situation, quantum models will not outperform classical model. That is the reality. But still, why we are exploring, why we are learning, because it is going to come in future. So we are getting ready with all our algorithms, models, and process. We are setting up the process. When we have the powerful quantum computer, that time we will be able to run these models there. That is the justification. So now you can see it is taking this much of time. Still, we are not getting the result. Let us wait for few more seconds. We will get it. In the meantime, please ask questions. I will answer. I am expecting a lot of questions. So by simulation only we can justify the concept. Yes, by simulation we will establish the process, how the quantum algorithm can handle machine learning models. That is what we can do. And you see here, it is giving 87%. In my observation, it is much better because sometimes I used to get 74, 63, all those things. And the given data where it is Virginica, it is classifying this as the versicolor. Because multiple times if you repeat, it may give you more near accurate result. So here we compare this classification matrix, this confusion matrix, this confusion matrix. Here only the Virginica went wrong. All other correct. Setosa and versicolor, they are correct. Only Virginica is classified as versicolor. That is the only mistake. But here in quantum, one Setosa is classified as versicolor and Virginica. One versicolor classified as Virginica. One Virginica classified as Setosa. Two Virginica classified as versicolor. That's the reason why the accuracy went very low. Now, is there any other question? Can we run the SVM model in IBM Quantum website? You can run, but you need the circuit, right? I will show the circuit. After seeing the circuit, you can take a call, because here, what is the quantum circuit? It is in the ZZ feature map, which particularly this ADAP feature map is the circuit. I will show you how I am telling that is the circuit. So, see here, if you print ADAP feature map, it will show this is the Qiskit circuit library data preparation ZZ feature map, ZZ feature map. So this is the circuit. So if you have circuit, you can draw. Here the another function is dir any object, that will give you the object model, all methods which you can execute on that operator or that object. So here you will see there is a draw and there is decompose. So what I'm going to do for this ad hoc feature map, ad hoc feature map, I am decomposing it. After that, I am draw the MPL format. Now you will see the circuit. This is the circuit. Yeah, you have to design this circuit in your circuit composer with the 4 qubit. Yeah, if you think you can design this circuit in IBM circuit composer, how will you give the input? The input you have to do manually, because in here you are using an abstracted class which is called QSVC, coming from Qiskit machine learning algorithms. But in circuit composer, you don't have those capabilities. So if you ask me, my personal suggestion, don't try this kind of abstracted or end-to-end solution in circuit composer. Circuit composer, you can experiment a simple circuit for as a validation or making sure that the operations are giving the expected result. Those kind of small operations only you have to explore circuit composer. For anything which you have the packages already, it is recommended to run on your Jupyter lab. That answer your question, sir? No open questions. Any other question now? If you change the kernels in SVM, yes. If you change the kernel, it may change, but which kernel we will change? So QSVM kernels here, what we are using, quantum kernel, which is fidelity quantum kernel. So obviously you should know what is fidelity quantum kernel. And fidelity quantum kernel, if you search and then go to the documentation, it will give you the explanation to fidelity quantum kernel, which is using the base state fidelity, which gives the overlap, state overlap of all the qubits. So it is using a kind of state overlap among all the qubits, and the feature map is helping us to cause that overlap. Then the compute and compute will perform the overlap calculation. So this kind of steps are here. In this one, the kernel, like in classical, whether RBF or sigmoid or any other kernel, they are not available here as such. Here, what you can do, you can, the feature map, you can manipulate. See here, it is linear, right? Instead of linear, you can put a full entanglement. And with that full entanglement, if you run, it may give some. See, now let me wait for a few more seconds. because now what I have changed, the feature map, I changed the entanglement. That is the one parameter what you can play around. Other parameter is the number of qubit. Obviously, that is also given by the number of independent variables. And then QSVC, it accept only two parameters. One is the kernel, other one is feature map. And if you see these parameters and then the values of parameters, there is no flexibility here in QSVC. If you are using Qiskit machine learning. Does it answer the question, sir? There is 3 more questions. As a complete beginner to quantum computing, where should I start? Okay, that is a good question. Very good. There are a lot of questions coming. Very nice. If you are a complete beginner, you have to start with IBM Circuit Composer, obviously. Before that, you have to understand mathematics for quantum computing and little bit physics, how the physical systems, quantum mechanics is operating those qubit states and how those quantum gates are transforming those gates. That is also you have to learn. And from the software side, you have to learn Python and Qiskit for general quantum programming and Pennyland for quantum machine learning. Let me type those things in the what is that one? I kept that PowerPoint. Here, let me put the point here because that will help you to understand the concepts. So, beginner, start with software ecosystem and hardware platform and little bit market and mathematics for QC, physics behind QC, then Qiskit, Pennyland, then yeah, these are the things you have to learn, and there are some good books. Let me type the books also. We'll type in the next one. You better start with applied quantum computing, applied approach, dancing with qubit, and by Robert Suter, and quantum computing for everyone. Then go to quantum computation and quantum information and theory graphical gate. So these are the 5 books which will give you a good understanding of the quantum computing. And if you want to learn the mathematics, there are specific books, mathematics for quantum computing, and for quantum mechanics, lectures on quantum mechanics. And there are few YouTube channels, 3 blue, 1 brown. 3 blue, 1 brown. Tube, potassium. So these are all various YouTube channel where you can learn other concepts, not quantum computing as such, but mathematics and then physics and historical events. Those things you can learn from there. And also we are conducting the basic course in 3 stages: stage 1, stage 2, stage 3. That stage 1 is a good starting point, which is 3 hours. That also good starting point. Like that, there are many other courses. There are the coding school, Q by Q, that is one course. And IBM has lot of IBM Qiskit courses. And every July, IBM will start quantum computing workshop or some other activity. Those things are good starting point. You can start. Does it answer the question, madam? Then how close is the simulator to the actual quantum machine? I would say it is not very close, because classical simulators, they are running on the classical system, so they won't have any quantum advantage, because being simulated there, it will not generate noise. But real quantum computers are noisy, because we are in this era. So the noise is generated randomly, and the closest capability are mathematical models. How the complex numbers are manipulated by unitary matrices. That is what you can build, you or what you can experience in the classical simulators. So they are not very close. If you ask for a number, some percentage, I can say 60 percentage, something like that. But performance, still you cannot reach the real QPU, because the parallel capacity is not possible. And next question, I was present throughout. How can I submit my attendance? They show the previous slide. Oh, previous slide. The beginners, this slide, sir. This one. Okay, I think that is the question. Um, okay, there is one question in the Q&A. Let me ask the Q&A question also. To get clarity or confident framing circuit, where to get the input? Usually, you will start quantum circuit for see, if most of the computer science professionals start with the machine learning, quantum machine learning. So quantum machine learning predominantly starts with the neural network, quantum neural network. So all neural networks are good starting point. But initially, if you start learning pure neural network, you will not understand the reason why we use those gates. So my personal suggestion is learn quantum algorithms. Quantum algorithms. There are 3 sets of algorithms. Basic. So these are all starts with the Deutsch-Josha algorithm, Bernstein, Vazrani, Simons. Follow this up, this order, that will be helpful. Then quantum Fourier transform, then quantum phase estimation, and Shor's algorithm, then Grover algorithm, then hidden shift problem. This is basic. Then for applications, predominantly optimization, which usually start with quantum approximate um, uh, quantum approximate approximate optimization algorithm, QAOA, algorithm, and variational quantum linear, sorry, linear solver and HHL, RO, Acidim, Lloyd algorithm, and variational eigen solver, and these are all for application. Next set I will put here. For QML, you have QSVM, QNN, QCNN, QGNN, QLSTM, QTL, QGON. Yeah, these are all popular quantum machine learning model. So if you start in this order, it will give you a way to organically learn quantum programming. But for your research purpose or in urgency, if you directly jump into QCNN and you miss all these algorithms and the mathematical model for those algorithms, QCNN will look like you will be able to tweak and you will be able to get some result, but you never understand how QCNN operates. So this is my personal suggestion, and this is how I teach to my mentees. Okay, hope this is useful. And let me check any other question. Okay, right. There is one more question here. Yeah, right. Okay, madam, hope you got the answer. I believe these questions are common to many of you. There are new questions. Please give the source to study QML algorithm. Oh, for QML, show the performance. Oh, you want to see the performance? So this is that performance, sir, for the QSVM. After changing to full entanglement, the accuracy reduced to 73. Remember, I told you it will come to 73 or 64. It is reduced to this one. But it classification is correct now. Virginica. Sir, this is the performance you wanted to see, right? Okay, right. Yeah, after the change. Yes, correct. You saw that one. So to answer the question, please give the source to study QML algorithms. Okay, right. That's a good question. Let me come back here and go to the books. Inside the books for QML, I recommend 4 books. Books by Maria Schuld, sorry, Schuld. Maria Schuld and Petrusano, they wrote 2 books. One is Quantum Machine Learning for Supervised Learning and Quantum Machine Learning for Unsupervised Learning. Those 2 books. And QML by Peter Vitek. And there is 2 more books, but they are specific to uh, finance domain. So that one is not suitable. There is one book by Frank, an ebook. Yeah. QML using Python by Sanjay Ganguly. Sorry, not Sanjay Ganguly. It is Oh my God, I forgot the book. Let me open the PPT because I had that PPT some time back. I conducted the session uh, for faculties through different uh, platform. Let me open this PPT because that PPT has all the books. Because I These are the four books I told for the book, and this should be the learning. This should be the learning path. You should start with the domain, then learn physics, then mathematics, then come to programming. After that, you stay in the programming. Python is for prototyping, but C++ and Julia for production. Then next one is for QML. It's taking some time to load. These are the books for mathematics. Yeah, these are the books for mathematics. And these are the books for QML. Machine learning with the quantum computers, quantum machine learning. Santanu Ganguly, sorry, I wrongly stated Santanu Ganguly. These are the books for quantum machine learning. And this is all books. Better you can take a screenshot. And I don't know whether I can share this PPT as it is. So you take screenshot, but I will paste these links in the chat window. Okay, there is a question. Which course we take learn quantum mechanics? Madam, you should know why you want to learn quantum mechanics, because quantum mechanics is wider scope, because quantum technology has many verticals: quantum computing, quantum communication, quantum sensing, quantum materials, quantum internet, quantum cryptography. Like that, there are a lot of things. Apart from these things, there are many quantum technologies. So if you want to learn multiple technologies, you should learn quantum mechanics. But quantum mechanics is somewhat advanced skill, and it is not necessary to become expert in quantum mechanics to understand quantum computing. So we can learn only selected concepts from quantum mechanics and focus on the quantum machine learning or quantum optimization or quantum cryptography or communication, whatever you prefer. So my personal suggestion, unless you are a master or doctor in physics, don't go for quantum mechanics. If you are from computer background, computer science or ECE or core engineering, better choose your domain, what I showed here. Like this, there are few domains. Based on the domain, you learn only those specific physics, not all quantum mechanics. That is not recommended because that will take a lot of time. Of course, it is an ideal approach, but we are already in a profession. We have a lot of professional commitment. Considering all those things, learning quantum mechanics is not okay. In that case, madam, you need not to learn full quantum mechanics, but only limited physics concept, and then focus more on the quantum machine learning. That is more suitable for your research. Hope that helps, madam. Sir, we cannot see your links. I pasted in the chat window, sir.
Sir, actually, it is posted back to the panelist only. So can you just select in the two option to everyone and then can you post, sir?
Which
Because
one?
I couldn't copy. Linear algebra full college course from that link, sir.
Oh, okay. That one I have to paste to all.
Post to
Oh, sorry.
panelists.
Oh, okay.
Everyone. Can you select everyone and can you post, sir?
Oh, okay. Now I understood what the mistake I made.
Yes, sir.
So
Thank you,
now
sir.
I pasted for everyone. Actually, there are a lot of concepts. So that is one thing with the quantum computing learning. You need a mentor to stop you. it is not like they will teach you more, but they will help you to stop. Don't go deeper into this concept because that is not going to help you. Indeed, that is what I learned from my mentors. I also used to, I thought whenever I come across a new topic, oh my God, I have to learn this one. I don't know. And like that, I used to read a lot of concepts. Then my mentor told KG, it is not possible for one person to become all concepts. You cannot become master of all topics in quantum computing. So choose, you are a data scientist, so focus on quantum machine learning. Unfortunately, I'm an applied mathematician, so I'm able to learn quantum optimization also. Now I'm working on quantum inspired. So my mathematics, since I studied applied mathematics and applied statistics, I'm able to easily learn those concepts. So if any of you from applied mathematics background, you will learn this concept very easily. Quantum machine learning research. What basics in mathematics, physics needs to be learned? That's a good question. I will give you the list. Mathematics. Should have a mathematics physics behind. Circuit encoding physics behind mathematics. To which batch I conducted mathematics? Okay, I'm not able to find it out, so I will type it from my memory. Let me go back to here. This is what, yeah, this is where I am typing. Later, I will share this PPT. So, mathematics. First, start with complex numbers. Complex numbers, linear algebra, particularly vectors, matrices, and decomposition. Then you should refresh your knowledge on groups, fields, space, subspace, then Hilbert space. Yeah, these are all sufficient, madam. Any other question? I believe most of the questions I answered. There is a good question. Please tell us the domains of research in quantum computing. Where our BTech be? Okay, the domains. Recommended domains. Quantum machine learning, obvious. This is the easiest one. Then quantum optimization. Then quantum inspired algorithms. Quantum cryptography. And yeah, these are the 4 things what students, undergrad students can jump in. There is one more thing, quantum finance. But this one is MBA students, not STEM background cannot do that one. But with the appropriate team, they can learn quantum finance also. And quantum chemistry is also a good field if the undergrad student is able to form a team from chemistry people. If you run a quantum algorithm in real quantum system, will provide greater accuracy. Yes, I observed that when I run, because I have a premium access to the IBM quantum computers with more qubits and less error rate. There I saw better accuracy than the simulator one. But still, when you compare or when you benchmark that with the state of the art classical, it is less only. So when you go for this, what are medical applications research going on now in quantum mechanics? In healthcare, instead of medical, I want to specifically tell about biotechnology. because as such medical is using only the machine learning models like prediction, classification, those things are all there. That is common. But the direct application of quantum technique or quantum mechanics is suitable for biotechnology. Then what is the need? Okay, I will answer that biotechnology question, then answer this question, sir. In biotechnology, protein prediction, okay, let me type it here because otherwise you will not. Biotech, protein prediction, protein folding, drug discovery, personalized medicine. These are all the verticals in biotech domain. Okay, now I will answer Santosh Kumar sir question. Then what is the need of quantum computing in machine learning? Sir, this question in 2025, the same question in 2016, the same question in 2036. Divide this into 3 time zones. In 2016, QML was introduced. The industry identified that quantum computing models can be used for machine learning also. That time, only support vector machine, quantum K neighborhood, and then quantum neural network is emerging. That time, the industry is skeptical about quantum machine learning models. But after 9 years, in 2025, we are seeing this much of quantum machine learning model. QSVM, QCNN, QGNN, QLSTM, QTL, QGAN, QRSC, quantum federated learning, like that, many models are emerging, which means the mathematical capabilities or computational capabilities of quantum computing are suitable for machine learning model because machine learning models are exponential problems, NP hard problems. The parallel processing capabilities of quantum computing is providing a solution. But still, quantum computers are in the early stage. We have only 1120 qubit in the superconducting and 5000 qubit in the quantum annealing. But QML model needs minimum 40,000 qubits. You understood, right? We need minimum 40,000 qubits, but we have only 1121 qubits. So there is a huge gap. That is the reason why the current quantum machine learning models are not able to compete with state-of-the-art classical models. But the moment we have 40,000 qubits, these things will start outperforming classical. So to answer your question, 2025 quantum computing or machine learning still question mark. We cannot build production systems. But when the industry grows and builds 40,000 qubits or above, we can start using quantum computing for machine learning model for production purpose. Hope that answered the question. There is one more question. ECE background, students and researchers kindly suggest current trends in quantum computing. See, for ECE background, the industry is, see, in the industry, they are looking forward or they are eagerly waiting for ECE students or ECE skill set, ECE domains, particularly control systems, circuit optimization, and characterization, measure testing and measurement. These are all various domains where ECE skill set is serving the quantum computing industry. And there is one more question. Hope that answered the question. Performance proportional to the number of qubits. Not only number of qubits, error rates in the number of qubits. That is one reason why Google Willow claimed more powerful capabilities compared to IBM, because Google has only 121 qubit in their Willow processor, but they claimed we run we give faster result, because the error rates are very less in the latest quantum computers. IBM is also working on reduced error rate for the fault tolerant systems, which is called Heron processor. See, now the Condor processor is 1121, whereas the Heron processor is only 433. But 433 qubit Heron processor is much accurate and powerful than 1121 Condor qubit, Condor qubit quantum processing unit. Then there is the last question: what type of project can we suggest for BE students having ML knowledge? Madam, these models associated with core engineering, for example, mechanical, civil, electrical, and finance, and medical, healthcare, and supply chain management, logistics. These are all various domain where the computer science students having machine learning knowledge can leverage their classical ML knowledge for building quantum machine learning models. So that is where we form a team with the core engineers, not just the computer science students, because computer science students good at programming, but the problem and formulation of mathematical model for the problem, that should come from subject matter expert who are core engineers. So usually we will do a subject matter expert from core engineering and a physicist for researching and mathematician for modeling. Then we will have computer science students to implement the mathematical model. So that is the mix of a team who are working on quantum solutions. So obviously it is not one-man show, and it should be a pure interdisciplinary skill set. And there is another question, two questions. Let me check. What are the quantum processor in simulation currently? Sir, for simulation, you can, let me type it here because that will be useful. Because most of the people knows only IBM Qiskit, right? Simulators. IBM Qiskit, Google SIP, AWS Packet, Microsoft UDK, and Microsoft Q Sharp, and Blockade, QRA Blockade, QRA Blockade, QLAX, and for Rigetti, Forest, E-Wave, Ocean, and IonQ is not available. There are Java-based simulators, but I don't remember their name. These are all popular simulators, sir. They are, why I am referring these simulators. If you build something on the simulator, you can run on the hardware also, because IBM, Google, AWS, QRA, Rigetti, Ocean, they have corresponding quantum computers. So if you build your solution on the simulator, you can run on the real quantum computers also. And these are all latest one. Older version, there is a J quantum. There is another language called QCL, quantum computing language. Those are all older simulators. They are not popular now. They are outdated. There are other questions. Okay. Jemi madam, hope I can share my contact number here.
Yes, sir.
Okay. This is my WhatsApp number, and if you want to email, this is my email ID. Yeah. And I am not asking only different simulators. Sir, different simulators means, does it answer your question or you need more information, sir? There is one question. How, Dr. C. Puspala, how can quantum computing overcome the challenge of quantum noise, error correction, and scalability to achieve practical real-world application? That is a great question, madam. Fortunately, yesterday I attended uh, IISc conclave in Bangalore. That is there. I realized that the hardware industry is making a lot of improvements to achieve these things. The quantum noise. There are uh, many control systems which are using machine learning to reduce the noise, and error correction also using machine learning. And error correction now they are just not only using Ancilla, they are also using um, the NV center in diamond, which is optical technology. So earlier it is superconducting technology, means all superconducting technology, but now the hardware industry is able to integrate hybrid approaches, meaning that a superconducting quantum computer supported by a nitrogen vacancy center based corrections. Like that, the industry is trying to integrate heterogeneous approaches to reduce the noise, improve the error correction, thereby increasing the scalability. And practical real world applications are available now in terms of special purpose quantum processing units. General purpose processing units are still in the development, but there are some special purpose, for example, a kind of quantum accelerators, which are similar to D-wave ocean, where they are using quantum annealing property for optimization problem. Like that, there are some special purpose quantum accelerators. They are giving the practical applications. Hope that answer your question. There are other questions. Very good. Uh, no. There are very questions. Better ask more questions. That is what the value. No, sir. Not at all. Please feel free to ask more questions. There is another question. India is it's really implementing hardware works using quantum circuits and applicable to 5G or 5BG. Sir, in this communication, there are many things happening with the optical fiber communication, and then optoelectronics, and as I told you, nitrogen vacancy based diamonds. Those are all happening. And particularly these researchers, as you know, National Quantum Mission has 4 T-Hub, right? IISc Bangalore is for quantum computing, and IIT Madras is for quantum communication, and IIT Mumbai for sensing, and IIT Delhi for materials, if I'm not wrong. But these are the 4 things. Here, the communication T-Hub is working on building quantum circuits for not only 5G, 6, 3BG, or the upcoming new models also. So the research is going on, but when it comes to the international standard, we are doing our level best. But you know, um, Europe, they built their first quantum internet, and NASA built their communication network using quantum computing, and China has built their um, quantum computing network. India has built its quantum computing network between Pragati Maidan and National Informatics Center, a 40-kilometer length. And there is a private company which was incubated in IIT Madras, QNU Labs, QNU Labs. They are making lot of good progress in communication side. So if you are interested in communication cryptography, QNU Labs is the organization where you can explore. Hope that answered your question. Can I move on to the next model? Okay, fine. So next model I want to show quantum convolution neural network, which I had. Is there in here itself I had. Is it 2501? Oh, that is there in my Linux system. Okay. Oh my God. Please give me a second. I have to pull it from. Yeah, here. But that is there in my Linux system. I will search here to see this. Okay. This one will have that QCML. Okay, right. It is Qiskit, but I want to have QCML using. Oh, sorry. Let me download this. This one. Come back to the Jupyter Lab. Yeah, here I will open the code. So I will explain this code because two models at least will be helpful. Here I'm using Pennylane. Here the model is pulling data for, this is COVID pneumonia normal data, chest X-ray. The data is a classical data. It is encoded into quantum using this circuit. Here you see the Quan V image that is calling a circuit. A circuit is RY rotation. Here you can see the circuit is RY rotation. So I am using angle embedding for encoding your classical image into quantum image. After that, what I'm doing, I'm having model. This model is a classical model, Keras model with the sequential and flat. I will create two models, quantum model, same classical model, but with a quantum data, and C model is the classical model with the classical data. And when I run this one, the green is the classical, blue is the quantum. So you will see the classical is, there is a, what is called, it is not, the convergence is not smooth, whereas quantum is promising the smooth convergence. And also, if there is a vanishing gradient, classical will get stuck, whereas quantum will overcome. That is what I observed in this model. I have run multiple with 300 epochs and all. That time I observed these things without what is called with gradient free models. Classical is outperforming but with there is a vanishing gradient, classical gets stuck, but quantum will overcome. So that is the advantage of quantum. There is the data and associated program. Uh, there is a question. Can you share this PPT on mail? I don't know, madam. You can get it. I don't know. You can get it from madam, Jemi madam. How to understand quantum image from classical image? Actually, classical image is zeros and ones, correct? Where in quantum, the the pixels are converted into rotation on a Bloch sphere. That is how it is working. And where are you using the quantum in CNN? You see the function I showed you, the this function, the quant image, where I'm calling the circuit. This circuit is having ROI rotation. You see here, QML. Yeah, QML is the device QML default qubit from penny lane simulator. Here it is rotating ROI rotation. Then there is a random line. So this is the quantum encoding of your classical images. That is the quantum part in this QCNN. There is one more QCNN, which is data also quantum, algorithm also quantum, but this is a research paper. There is no implementation for that one. Only mathematical model was released. One of my mentee did working on that one. So I cannot share more detail about that quantum approach, but it is there in the uh, market or in the research. There is a question. Uh, mm, Means each pixel in one Q state. No, not each pixel in one Q state. One qubit can have multiple pixels because it is just rotation only. So because of the rotation, and moreover, when we are adding multiple images, they are all added into one density matrix. It is not just one qubit. When there are more than one qubit and when they are in the superposition mixed state, we have to use density matrix. State vector is not sufficient. So inside the density matrix, the pixels are encoded as the quantum data. That is what happening here. Okay, there is some question in the Q&A. Sir, share the physics, how to reduce the noise in QML model output and also get consistent output. Currently, is it possible to get output without noise? No, currently it is not possible to get output without noise because we are in Niskera quantum devices. So if you want to reduce the noise in QML, choose the QPU which has the better error rate. When I say choose the QCL, choose the QPU, remember, oh my God, where is that circuit? I had that circuit, right? Must be here, not here, not here. I think it must be here. Oh my God. I missed that somewhere in the. Let me check here. Submit finding web elements. It might be here. Here when I go to my platform, in the platform, when if you scroll down, you see the all QPUs. Here in the QPUs, you can see their spec. In the spec, they will mention, see TQ error, best and layered 2.07 or minus 00, sorry, 0.00027 like that. So this will give you the error rate of the QPU and the number of qubits and error rate, it will result in the CLOPS. So CLOPS is a function of qubits and error rate. So you can see here, some of the systems will have higher qubit but less CLOPS. because their error rate is low. So by analyzing these things, you will be able to understand which QPU is suitable for your tolerance. Whatever tolerant your model allows, you can choose that one. And physics domain, so in the physics domain, actually, indeed, physics is the foundational. Oh, like mathematics, you need the list of physics concepts. I think you are asking for that question. The physics domain, it's not coming. I will answer later. How can quantum computing overcome the challenges of quantum noise? That I answered. And if quantum and quantum related things not exist or not coming up only, then which one over learned the quantum process? Um, Sir, actually, uh, they are existing. It is not that they are not existing. They are in the nascent stage and then coming up, and they are growing day by day. So it is an emerging technology. As of now, we are not having the relevant accuracy or reduced error rate or stability. Those things we are not having now. But as the industry matures, it will reach a stage. The industry prediction is 2027, we will have more stable quantum processors. And 2035, we will reach 10,000 logical qubits and more than 40,000 physical qubits. We will reach there. So there is a report from Boston Consulting Group. They divided the quantum computer generation into three generations: 2018 to 2028, first generation; 2028 to 2039, second generation. But third generation starts from 2031. 2031 to 2047 is the third generation. If you see second generation, the third generation, there is a overlap of 7 years. 7 years, 9 years. So the overlap on the technology and software solutions are 9 years. Within that period, we will see a lot of industrial production quality solutions. So we this to answer the Parthasarathi question, they are existing now, but not to the required quantity and quality, which is improving year by day. I would say day by day, because I am observing this industry since 2004, when IBM had only 5 qubit NMR system, but now IBM has 1,121 superconducting qubit. Superconducting is the one of the difficult physics system to build. NMR is easiest one because it is MRI scanning based thing. But superconducting, going to cryogenic, using cryo and going to the microkelvin temperature and then controlling the Cooper pair or Josephson junction, those are all existing now. The industry is able to achieve that one within this 20 years. So another 7 years, we will see real working quantum computers which can be used for production purpose or real world application purpose. Okay. Let me answer all the questions like that. It's not remaining here. I have to answer one more question. The physics domain. Let me type here because physics domain, the questions here. So like mathematics, I will put it here because next to mathematics, I will put physics. And again, I'm typing from my memory, so I may miss few concepts. So, for conducting. trapped ion, photonics, nickel atom, and quantum annealing. These are the 5 types of quantum computers. Then NV center diamond. This is one technology what you have to learn. And usually postulates of quantum mechanics. There are 6 postulates that we have to learn. And standard model of particles, which says about quarks, quarks, leptons, bosons, then muon, neutrino, and anyons. All those things are falls under the standard model of fundamental particles. Let me put it fundamental particles. This is the latest one, 1960 model. That is the reason that deals with the fundamental particles. And cryogenics, optics, and yeah, these are the things coming to my mind, but there are many things. I hope this is helpful partially. Okay. Is there any other question? Great. There is a one question. Did I miss anything? Yeah. So we are encoding. See, the encoding quantum is very important thing because there are 4 types of encoding, like basis encoding, angle encoding, amplitude encoding, hybrid encoding. So depending on your problem domain, you have to encode your classical data into quantum data, quantum systems, which is complex numbers, which is used to represent amplitude or angle of your system. Then that will work. That is the encoding system. Oh, okay. Sorry. I'll type here. This is encoding. Encoding. Amplitude encoding. Hybrid encoding. In the physics concept, you have to understand very importantly density matches. This is very, very important. And state vector. I don't know whether to put this in mathematics or physics. They are mathematical model for physical behavior. Okay, right. I think we are 9 o'clock at the time. Yes, sir. Yes, sir. This is the encoding, sir. Yeah, this is that slide, sir. Madam, if possible, I will share this updated PPT with you, madam. Please share with all faculties. It will be
Yeah,
helpful.
sure, sir. Sure,
Because
sure, sir.
I took lot of notes based on the questions. And
Okay.
personally, I feel that this kind of question and answer more valuable compared to pre-prepared PPTs. That's the reason why I keep a lot of time for Q&A. Madam, that's all from my side. If no more questions, I'm hand over to you. Thanks to all your engaging, amazing audience. I'm looking forward more research work because I am into the research. My area is quantum machine learning, optimization, quantum inspired, cryptography to some extent. I have other researchers who will work with the cryptography projects. That's all from my side. Thanks for the opportunity. Thanks, madam. Thanks for all audience. Thank you.
Sir, 1 minute. On behalf of Cardiac Institute of Technology and Sciences, I express my gratitude for accepting our invitation and deliver your expertise with us today, sir. You have motivated our participants and provided a lot of useful materials and resources for further learning. I hope this session was very useful to our participants. Sir, you have addressed all the basic knowledge which is required in quantum computing for implementation, and you have explained everything in a very simple manner. Also, you have addressed all the questions of our participants with the sufficient details. And thank you so much, sir. And all the hands-on sessions and demonstrations which made a significant impact and understanding for all the participants. And all the explanations are crisp and clear. Thank you so much, sir, for
Thank
sharing
you.
your valuable time. I
Thank
hope
you.
the participants also happily traveled with you throughout the sessions. Thank
Thank
you
you.
once again, sir. Thank you. Thanks a lot.
Thanks,
Sir,
madam.
you can
Thank you.
disconnect, sir. Thank you. Thank you, sir. Bye, sir. Good night.
Good night.
Participants, the attendance link is posted in the chat screen. Kindly fill your attendance. Kindly fill the feedback form. Thank you, participants. You can leave after marking your attendance. There are many more good sessions are there. Kindly stay back for future sessions as well. Thank you so much. Good night. And those who have marked the attendance, you can leave. Thank you all. Thank you. Yeah, we'll share the PPTs. Yes, sir. Really, really. Thank you. After marking the attendance, please leave from this link. Kindly mark your attendance in the link given in the chat box for recording your attendance. Yeah, sure, sure, sure.